that I've been talking about. So first we derived the constant overlap add property for windows in the time domain as being the Fourier dual of the Nyquist property in the frequency domain, where the zero crossings had to be at the non-zero multiples of 2 pi over r, or harmonics of the frame rate. And now we've got the dual of that, which is that if we've got a Nyquist property in the time domain, we have a perfect reconstruction filter bank in the frequency domain. So here's kind of some notation for that. So in the time domain, Nyquist at multiples of capital N corresponds to a frequency response that is constant overlap add for spacings 2 pi over n. And that's what we just derived. That's the filter bank summation dual derivation to overlap add. So this is just another example of this precise duality between overlap add and filter bank summation. So now the dual of this whole line here is this line. So the window being constant overlap add at a hop size of r corresponds to, in the frequency domain, the window transform being Nyquist of 2 pi over r. So zero crossings at non-zero multiples of 2 pi over r. So that is the overlap add case. And these are if and only if relations. So if you have a constant overlap add filter bank, then you have the Nyquist property in the opposite domain. And so you can argue that, well, in practice we really want both of these. We want constant overlap add in the time domain, and we want constant overlap add in the frequency domain. So that translates to a pair of requirements on your window, that it be Nyquist of capital N in the time domain and Nyquist of 2 pi over r in the frequency domain. All right, so that's some good duality between overlap add and filter bank summation.